The number 6 bare grounding electrode conductor connected to the power company's ground wire on the pole is not an acceptable grounding electrode conductor for a service. According to the National Electrical Code, (NEC), a grounding electrode system must include at least one of the following: a ground rod, a driven pipe, or a plate electrode. In addition, the grounding electrode conductor must be connected to the grounding electrode system and extended to the service panel. Your practice of grounding the neutral in the meter can and extending an insulated ground wire into the panel is correct. The jumper between the neutral bar and ground bar in the panel should not be left in place if the neutral is grounded in the meter can. The panel should be bonded to ground using the bonding screw. The purpose of grounding the neutral in the meter can is to establish a solid grounding path for the service. However, leaving the jumper in place in the panel would defeat this purpose by allowing current to flow on the neutral conductor instead of the grounding electrode conductor. This could pose a safety hazard. To elaborate further on grounding electrode conductors, let's delve into the specific requirements outlined in the NEC. Section 250.50 covers grounding electrode systems, emphasizing the need for a comprehensive and effective grounding path. This section mandates that all grounding electrodes present at a building or structure must be bonded together to form a unified grounding electrode system. This interconnection ensures that all available grounding paths are utilized, minimizing potential differences and providing a low impedance path for fault current. Permissible grounding electrodes include metal underground water pipes, metal frames of buildings or structures, concrete encased electrodes, ground rings, and rod and pipe electrodes. Ground rods, typically made of copper or copper-clad steel, must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. The NEC specifies the minimum diameter for ground rods depending on the material. For example, copper ground rods must be at least 5/8 inch in diameter, while steel or iron ground rods must be at least 3/4 inch in diameter. When multiple ground rods are used, they must be spaced at least 6 feet apart to avoid reducing their effectiveness. The purpose of spacing is to ensure that each rod is in contact with undisturbed earth, maximizing its ability to dissipate fault current. The grounding electrode conductor, which connects the grounding electrode to the service equipment, must be sized according to NEC Table 250.66. This table bases the conductor size on the size of the service entrance conductors. For example, if the service entrance conductors are number 2 American wire gauge or AUG copper or number 1/0 AWG aluminum, the grounding electrode conductor must be at least number 8 AWG copper. If the service entrance conductors are number 3/0 AWG copper or 250 kcmil aluminum, the grounding electrode conductor must be at least number 6 AWG copper. For larger service entrance conductors, the grounding electrode conductor size increases accordingly. It's crucial to select the correct size grounding electrode conductor to ensure that it can safely carry fault current back to the source. Improperly sized grounding electrode conductors can overheat and potentially cause a fire or other safety hazards. The NEC also addresses the installation of the grounding electrode conductor. Section 250.64 specifies that the grounding electrode conductor must be securely fastened to the surface on which it is carried. It must also be protected from physical damage. When the grounding electrode conductor is exposed to physical damage, it must be installed in rigid metal conduit, intermediate metal conduit, electrical metallic tubing, or other approved raceway. The raceway must be bonded to the grounding electrode conductor at both ends to maintain the integrity of the grounding path. Now, let's discuss the proper grounding and bonding procedures for meter cans and service panels. As mentioned earlier, it's a correct practice to ground the neutral in the meter can and extend an insulated grounding conductor to the service panel. This approach helps to establish a solid grounding path for the service and minimizes the risk of neutral current flowing on the grounding conductors. In the meter can, the neutral conductor is typically connected to the metallic enclosure of the meter can, which is then bonded to the grounding electrode system. This creates a direct path for fault current to flow back to the source, tripping the overcurrent protective device and de-energizing the circuit. When extending the grounding conductor from the meter into the service panel, it's important to use an insulated conductor. This prevents the grounding conductor from coming into contact with other metallic objects and creating unintended ground paths. The grounding conductor must be sized according to NEC Table 250.122, which bases the conductor size on the rating of the overcurrent protective device protecting the circuit. For example, if the overcurrent protective device is rated at 20 amps, the grounding conductor must be at least number 12 AWG copper. If the overcurrent protective device is rated at 60 amps, the grounding conductor must be at least number 10 AWG copper. For larger overcurrent protective devices, the grounding conductor size increases accordingly. In the service panel, it's crucial to remove the bonding jumper between the neutral bar and the ground bar. This prevents neutral current from flowing on the grounding conductors and ensures that all fault current flows through the grounding electrode system. The service panel should be bonded to ground using the bonding screw, which connects the ground bar to the metal enclosure of the panel. This creates a direct path for fault current to flow from the panel to the grounding electrode system. It's important to note that the neutral conductor should be isolated from the metal enclosure of the service panel. This prevents neutral current from flowing on the enclosure and creating a shock hazard. The neutral conductor should be connected only to the neutral bar, which is insulated from the panel enclosure. To further clarify the importance of these grounding and bonding practices, let's consider a scenario where a fault occurs in an appliance connected to the electrical system. If the appliance has a faulty ground, the fault current will flow through the grounding conductors back to the source. If the grounding system is properly installed and maintained, the fault current will quickly trip the overcurrent protective device, de-energizing the circuit and preventing a shock hazard. However, if the grounding system is not properly installed or maintained, the fault current may not trip the overcurrent protective device, and the appliance enclosure may become energized. This could create a dangerous shock hazard for anyone who comes into contact with the appliance. Therefore, it's essential to follow all applicable grounding and bonding requirements to ensure the safety of the electrical system. This includes using the correct size grounding electrode conductors, properly installing and maintaining grounding electrodes, and isolating the neutral conductor from the metal enclosure of the service panel. In addition to the NEC requirements, local codes and regulations may also apply to grounding and bonding practices. It's important to consult with a qualified electrical inspector or engineer to ensure that the electrical system meets all applicable requirements. Maintaining a safe and effective grounding system is an ongoing process. Grounding electrodes should be periodically inspected to ensure that they are in good condition and properly connected. Grounding conductors should be checked for damage and replaced if necessary. Any modifications or additions to the electrical system should be made in accordance with the NEC and local codes. By following these guidelines, one can help ensure the safety and reliability of the electrical system and protect people from electrical shock hazards. Proper grounding and bonding are essential for electrical safety. They provide a low impedance path for fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. This prevents electrical shock hazards and protects people from injury or death. Neglecting grounding and bonding requirements can have serious consequences, including electrical shock, fire, and equipment damage. Therefore, it's crucial to follow all applicable codes and regulations to ensure that the electrical system is properly grounded and bonded. It is also essential to understand that the power company's grounding system is designed to protect their equipment and personnel from high voltage faults. While it provides a certain level of safety, it's not a substitute for a properly installed and maintained grounding electrode system for the service. The power company's ground wire is typically connected to a grounding electrode at the pole, such as a ground rod or a buried ground wire. This grounding electrode provides a path for fault current to flow back to the substation in the event of a high voltage fault on the power company's equipment. However, this grounding electrode is not designed to protect the customer's electrical system from low voltage faults. Therefore, it's essential to install a separate grounding electrode system for the service to provide adequate protection. In summary, a number 6 bare grounding electrode conductor connected to the power company's ground wire on the pole is not an acceptable grounding electrode conductor for a service. A proper grounding electrode system must include at least one of the following: a ground rod, a driven pipe or plate electrode. The neutral conductor should be grounded in the meter can, and an insulated grounding conductor should be extended to the service panel. The bonding jumper between the neutral bar and ground bar in the service panel should be removed to prevent neutral current from flowing on the grounding conductors. The service panel should be bonded to ground using the bonding screw. By following these guidelines and adhering to the NEC and local codes, one can ensure the safety and reliability of the electrical system. Remember to consult with a qualified electrical inspector or engineer if there are any questions or concerns about grounding and bonding practices. They can provide valuable guidance and ensure that the electrical system meets all applicable requirements. Electrical safety is paramount, and proper grounding and bonding are essential components of a safe electrical system.